We're going to look at H.225 trunk types. Okay, so H.323 has the control protocol. H.323 is really a suite of protocols, of course, not a protocol itself. But H.225 is the control protocol. We won't look at H.245 today. We looked at that yesterday in regards to, median, MTPs, and things like that. But H.225 trunk types, we have a H.225 gatekeeper controlled trunk, and we also have an intercluster gatekeeper controlled trunk. We also have an intercluster non-gatekeeper controlled trunk, but we're not going to deal with anything outside of gatekeepers today. So an H.225 gatekeeper controlled trunk is typically used if you're building a trunk to an endpoint that's a non-Cisco or unknown vendor, type of a gateway, or gatekeeper controlled, whether it's Cisco or not, but the far end of that. Okay, so whoever the gatekeeper routes us to. So even if the gatekeeper is a Cisco iOS gatekeeper, maybe under our administrative control, the far end that we're going to eventually get routed to is not a Cisco or an unknown vendor gateway. And so we use this possibly in the case of forming a trunk to maybe say, for instance, an H.323 ITSP, or Internet Telephony Service Provider. Okay, then we have the gatekeeper-controlled intercluster trunk. So this really is based on, as we mentioned yesterday, H.225, or H.323, and we use this if we're building a trunk to an endpoint that is Cisco hardware or software. So for instance, in the case of forming a trunk to another CUCM cluster or CUCME, another way of saying Call Manager Express. Okay, so basically this is H.225 with enhancements, Cisco proprietary enhancements. And actually there is auto protocol design within CUCM that can sense if the other side is a older format, maybe say, I believe it was prior to CUCM 3.1 that we needed to, between clusters, use an H.225 trunk versus an intercluster. And so, maybe we're integrating, for whatever reason, a 7.0 cluster with a 3.0 or a 3.1 CUCM cluster. We could build an intercluster trunk, and it will actually fall back to H.225 only. So there's intelligent auto protocol sensing within CUCM. That's covered in the CUCM SRND. As we mentioned with all of the deep dives, and as we've been doing, we will continue to rely much less on death by PowerPoint, so PowerPoint slides as we have here, and much more so on during the actual presentation of the demonstration of the technologies and implementation of the tasks, we'll rely much heavier on the actual Cisco documentation. One, because it's really good for you to know where it is, how to use it, what is available at what locations. Two, because you have that documentation available to you in the CCIE Voice Lab, if that's why you're here. So whether you use it for, even if you're not here for the lab, or after maybe you say, well, once I pass the lab, I'm going to go back to doing searches on Google, you'll actually find that once you've passed the CCIE Voice Lab or any Cisco CCIE lab, you will have studied so much with learning the structure and hierarchy and how to navigate the Cisco documentation website and solution reference network designs, or SRNDs, that you'll actually primarily go there for all of your information. And it's only when you maybe can't find something within that that you might do a search on probably Cisco supportforums.cisco.com. So supportforums.cisco.com used to be called NetPro. I think it's now called the Cisco Online Support Community. And then maybe, tertiarily, go to Google or Bing. Okay, so you will find that the Cisco documentation website will be your primary source. So first of all, let's just take a look at some basics, real basics of what even is a gatekeeper. Gatekeeper is sort of the sat nav, or in the US people might call it a GPS, kind of a directional guide, kind of a road guide. Another way of looking at it, and this is the way I prefer, is Gatekeeper is sort of the DNS server of the H.323 VoIP world. Okay, so let's take a look at this. What can be routed on an IP network? The answer is IP addresses. Can we route host or domain names? No, we need IP addresses. Okay? That's what we actually route on the IP network. Even if we're getting a domain name or host name resolved via DNS, we have to know the what? The IP address of the DNS server to route that request to, right? We cannot say, hey, give me the IP address for cisco.com, and the DNS server should be dnsroot.dns.org. That doesn't work. We have to have an IP address for the DNS server so that we know who to route to. And DNS servers then have forwarders, and we can have backups. Okay, so what do DNS servers resolve? They resolve IP addresses in exchange for fully qualified domain names in a specific zone. Okay, so you give the DNS server a fully qualified domain name, and it gives you the IP address of the endpoint that you wish to contact. Right? Gatekeepers are really no different. What do they resolve? They resolve IP addresses in exchange for E164 phone numbers in a, hey, just like DNS, in a specific zone. Okay, so just like we give a DNS server a fully qualified domain name and it gives us an IP address of the endpoint we wish to contact, with Gatekeepers we give it an E164 phone number and it gives us the IP address of the endpoint we wish to contact. Sounds fairly similar, huh? Really, if you look at the heart and basics, if you boil it down to the basics, that's what a gatekeeper is. It's there for IP address resolution. So why would we use it? You know, why wouldn't we just have, as we mentioned, H323 peer-to-peer endpoints are intelligent and they can have a full dial plan of everyone that could possibly be reachable on this IP H323 network, right? They could. That's kind of like the analogy of saying every Cisco IP phone should have a complete dial plan. So every time we change the dial plan, we have to push it down to all of the IP phones, which incidentally we can do that with SIP phones, but we cannot do that with skinny phones. But even if we did want to do that with SIP phones, and we'll talk about the merits and how and why on another day for that, if we did, it becomes slightly unmanageable. And as long as we're able to push them to all the phones, it's somewhat manageable, but we still have to have some sort of central server. If every endpoint, let's say every Cisco IP phone was truly peer-to-peer, had absolutely no idea of a central server, or let's just take it even in a different direction. Let's say that we had, more specific to gatekeepers, let's say that we had, in fact I did a installation many years ago now for a school system, and they had about, I think they had actually 42 routers connected at each of the school sites in this district, and they were each providing, there was no CUCM or CME, no central server of any type, no skinny signaling. It was strictly toll bypass. They had all these Tataran, Coral, PBXs, and they decided that they wanted to basically network them all together over this advanced IP network that they had just built. And they set up all these gateways. So we had 42 gateways. So each gateway had to have a full dial plan, full sets of dial peers for every other gateway. And every time we would add one in, we would have to go back to all 42 gateways and update. Well, first of all, we'd have to copy all of the dial peers, change various variables, and paste them in the new router. But then we'd have to go add the few. There was typically about 3 to 4 separate routes or dial peers that were needed for each school site. So we'd have to go to 42 routers and add 4 dial peers each, right? So we're talking over 160 dial peers plus the that we had to add amongst the existing sites. And the existing sites already had 200 plus, believe it or not, 200 plus dial peers. So then we had to add those with changing the variables to the new site as well. So we were adding or making changes to upwards of 350 to sometimes 400 dial peers for every single new school site that we brought on to the toll bypass network. So I had proposed, and finally they went along with the idea of saying, guys, this is not only extremely administratively burdensome, and you're paying my consulting fees and a large amount of hours for every single time we want to add new dial peers, and there's so many dial peers, and we have to double, triple check our work, because when you're adding that many dial peers, 350 to 400 dial peers, there's definitely room and likelihood at that point for human error. Keying in a wrong variable or putting in something and it doesn't work, and maybe I have to come back out, and it just lends itself to a very large administrative problem and sometimes even nightmare. So instead, finally, they went along with the idea of purchasing the license for a couple of redundant gatekeepers. We'll look at redundancy today. And that basically took 200 dial peers, 200 plus dial peers at every site, so 40-some sites, down to 1 dial peer per site. And so every time that we'd add a new site, it would pretty much be a cookie cutter copy and paste of the template. I mean, changing some IP addresses and various things, but there was only 1 dial peer, because that dial peer would point to RAS. And what did RAS point to? We'll look at session target RAS. Session target RAS points to whoever I am as a gateway, whatever gatekeeper I am registered with. Send all of your traffic there. And it becomes the traffic cop. It becomes the DNS server of the H323 world, that every single time I need to route a call to a specific E164 phone number, I simply give that to the gatekeeper. And just like a DNS server would give me an IP address back in exchange for a domain name like cisco.com, because my workstation cannot route to cisco.com, it routes to an IP address of a web server. In the same way, I give the phone number I want to call to the gatekeeper, the only gatekeeper I'm registered with, because gateways can only be registered to 1 gatekeeper at a time, with the somewhat pseudo exception of clustering and alternate gatekeepers. We'll talk about that and do that configuration today. But aside from that, from a basic standpoint, I can only register with 1, at least primary gatekeeper at a time. Okay, so I hand my phone number to the only gatekeeper I'm registered with, and what does it do? It gives me a response of an IP address, and I contact that far inside. We're going to take a look at that exchange. That's the admission of RAS. So we're going to take a look at our initial topology. Our initial topology is going to be that we're going to have this gatekeeper, this DNS resolver for phone numbers, as a single router. And it just so happens that in today's lab we're going to use, to begin with, our corporate headquarter router, which happens to be, okay, so here's our gatekeeper, happens to be at the same physical site as the corporate headquarters CUCM cluster. It doesn't have to be in any way, but that's where this one happens to be. And we're also going to register our branch 1, I'm sorry, that should actually say branch 2, typo in my slide, our branch 2 CME gateway as our as a second gateway, but to the same gatekeeper. Okay, the one that happens to be at corporate headquarters. Again, positioning of the gatekeeper, where on your IP network it is, might have implications to design, but that's not really what we're here today to discuss. We're here today to discuss the technology and how gatekeepers are implemented. So IP addressing, as long as everyone has, as long as this gateway and this cluster, which is looked at as multiple gateways, has network layer reachability, or IP connection I can ping and route to wherever this gatekeeper is, then it really doesn't matter where the gatekeeper is. And so within a gatekeeper, we have these idea of zones. We mentioned that just like a DNS server might have different zones, a gatekeeper can have different zones. So here we've got the zone called SEA, because our corporate headquarters site is in Seattle, Washington, US. And then we have zone AMS, because our branch 2, again, forgive the typo, our branch 2 CME router is actually in Amsterdam, Netherlands. And so we've got 2 separate zones. So what are zones? Well, just like DNS, they're just logical partitions. Okay? They're just sort of a way of partitioning up the information or types of endpoints that get registered to a gatekeeper. So let's discuss the 5 basic pieces real quickly of an H323 network, the 5 different types of sort of endpoints, if you will, or devices. We first have gateways. Gateways tend to, H323 gateways tend to define a device that stands in the way and proxies on behalf of multiple other devices. So for instance, our branch 2, again, forgive the typo, our branch 2 CME router is going to proxy on behalf of something that's not seen up here, which is all of our Cisco IP phones registered to the CME router. Okay, our corporate headquarter CUCM cluster, we have a pub, a publisher, and a subscriber server. So those will be looked at as 2 separate gateways, but registered to the same Seattle zone. And those gateways proxy on behalf of, again, not pictured, all of their Cisco IP phones. Okay, so that's the idea of gateways. Then we also have the idea in the H323 world of what's called a terminal. A terminal tends to be, and again, this is not a hard, fast rule. It's more of a loose recommendation, because as we'll see, we could register CUCM cluster as a terminal. Not really recommended, but look at that. A terminal tends to be something that registers, first of all, a terminal tends to be something that needs a gatekeeper to route, not always, but tends to be something that basically has one device that it's tied to. Something that is a good example of a terminal-only device was the old, and you may not even remember this if you haven't been around voice for a long time or haven't ever worked with them, and I bless you if you've never had to work with them. The Cisco ATA, or analog telephony adapter, analog terminal adapter. That could connect 1 or 2 analog, regular, dumb, FXS phone devices. Okay, and so it was a terminal only. It basically represented 1 extension or possibly 2 extensions, but it wasn't proxying on behalf of, like CUCM cluster, maybe thousands of extensions, or even CME, possibly hundreds of extensions. Okay, so we've got a gateway, we've got a terminal, we've got something called an MCU, or a multi-point controller unit, also known as a conference bridge. Again, within the new ways of our unified communications networks, we tend to register those to CUCM cluster, but before CUCM cluster and still supported, we could register H323 only MCUs directly to a gatekeeper, and then other endpoints such as gateways and terminals could make use of that conference bridge or multi-point controller unit. Then we've also got something called Gatekeeper as our 4th endpoint or type, and then we've got something as a 5th type called a proxy, H323 MCM proxy. So we actually don't use MCM proxies at all anymore. And the reason is that we've got something in the industry called session border controllers. Cisco calls their brand the Unified Border Controller, or the Cube, the Cisco Unified Border Element. Okay, so, and we'll take a look at that on a complete different day, and when we look at that, we will also look at bringing Cube into a gatekeeper-controlled environment. But we're not going to look at Cube today with Gatekeeper, just because we have so much on the basics, advanced and expert level understanding of Gatekeeper itself to talk about. So those are the 5 pieces: Gatekeeper, Gateway, Terminal, and then things that we don't typically use too much anymore, which are our MCM proxies and then our MCUs. In fact, terminals we don't even register too often to Gatekeeper anymore. If we use them, we register MCUs and terminals directly to a CUCM cluster or a CUCME. Okay, so getting back to zones. Zones are just a logical way of partitioning up what type of endpoints, like gateways primarily, that we want to register to the local administrative or authoritative control of a gatekeeper. So both of these zones that you see here are what are called local zones. That is, they are locally controlled by, and they are under the authoritative control of this gatekeeper. We're going to register our CME router to the Amsterdam zone and our CUCM cluster of 2 gateways to the Seattle zone. Okay, that's going to be our initial topology, and we're going to look at pretty much most all of our complex. In fact, we might even boil everything down to one zone, one single zone, so delete the other if we have time, and look at some complications that could get added if we only had one zone. You'll see why 2 zones makes it a little nicer sometimes. But then after we've looked at pretty much all of our advanced and expert level configuration and debugging, troubleshooting, and full understanding of how a single gatekeeper routes calls for admission requests, and we'll also talk about all the different RAS messages, then we might go on and take a look at, hopefully we'll have time to do this, I'd like to get into a clustered topology as kind of a last thing that we'll look at. So once we understand everything, now this isn't what's called local and remote zone. We could look at that if we have time. That's actually not very difficult at all. It's just 2 gateways registered to 2 different gatekeepers, and they're exchanging messages back and forth between each other. We might have enough time to look at that. That's not nearly as complex. It pretty much doesn't go too far beyond a regular 1 gatekeeper. But then a much more complex topic to talk about, and I'd like to hopefully fit it in, is clustered topology. So looking at gatekeeper clusters with the GUP, the Gatekeeper Update Protocol, and to the gateways, what are known as an alternate gatekeeper. So in this kind of a topology, what you'll see is that the corporate headquarters CUCM cluster, pub and sub, register with their local gatekeeper in the local zone of Seattle. But because this gatekeeper is clustered together with the gatekeeper over at router 3, the branch 2, again, forgive the typo, this says branch 1, but it will be branch 2 we're working with today. That in the slides before you look at those recorded sessions. But the router that happens to also be the CME router, we know it as branch 2 router 3, will also be a gatekeeper. So if it's the same exact physical device, why did I draw it as 2 separate logical devices? For that reason exactly. When we're looking at technologies, it can sometimes, in fact very often, especially if we're just learning and beginning to understand the technology, it can be very confusing to say, hey, this device, this branch 2 router 3 happens to be a CME and a gatekeeper. You say, oh, well then it would automatically register with itself. Well, no, not at all. In fact, it could be a gatekeeper that provides registration for other gateways, and this branch 2 CME router registers with the headquarter router. Okay, so we could get into complex things like that, not trying to confuse you and throw you off there, but the idea is it's always a good idea to draw out our topologies as logical topologies and define logically separate server mechanisms as separate kind of drawing entities on our Visio or PowerPoint or whatever kind of drawing we're doing. That way we can see that it's not CME that's clustering with the corporate headquarter gateway. It's the branch 2 router Again, forgive the branch 1 nomenclature there, but it's the branch 2 router gateway that's clustering with the corporate headquarter gateway, and it just so happens that the branch 2 CME is registered to the branch 2 gatekeeper. Okay, it's always good to draw these logical separations. So we'll see the branch 2 router registered with the zone called, Amsterdam there, or AMS, there on the branch 2 gatekeeper. Now what you're going to see is, because we're going to issue clustering, when I register the corporate headquarter gateways, CCMs, with the corporate headquarter router gatekeeper in the local zone called Seattle, it will automatically also pass that information across to the zone Seattle Gatekeeper 2, which is kind of a backup zone on another clustered gatekeeper. Okay, we become part of a true cluster, and we pass state information or stateful information. And likewise, the CME on branch 2 will register with the local branch 2 gatekeeper in the zone Amsterdam, but will also automatically be registered with the corporate headquarter router in the backup zone called Amsterdam Gatekeeper 1. Okay, we'll see how this works. We'll see how the naming is. We'll take a look at all the endpoints and try to route calls just as we did with our initial topology. So we have the ability to provide a, and all this was done without configuring anything on corporate headquarter to tell it to also register with another IP address. This is all done just between the gatekeepers themselves through the clustering GUP protocol. We have this ability to have really stateful or high availability failovers, especially when we have multiple clusters. We also have the ability, we won't look at it today because we don't have two routers at the same site. The only same subnet that they share is a serial link, and that could just get confusing. But also, I don't know if we'll have enough time to. If we do, we could go into it at the end. But we also have the ability to have redundancy or resiliency with gatekeepers local to a site with HSRP. So I could have two gatekeepers running the exact same configuration and have HSRP configured between them, and whoever, so this is another not pictured gatekeeper here, whoever was the active state HSRP router would be the one that was handling the requests. And of course, the corporate headquarter cluster would know about the virtual IP that both of them share. Same thing at the other site. So that's another way to actually add and we'll whiteboard this, but a third level of maybe redundancy and resiliency is to have actually clustering and HSRP. Okay, so you get extremely high availability, 5 nines,